Hi, and welcome to the class on probability as part of the Statistical Inference class in the Coursera Data Science series. My name is Brian Caffo, and this class is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Bloomberg School of Public Health. In this lecture, I'm going to cover probability at a very basic level, just enough for what we need in the data science specialization. I have a more in-depth treatment in my Mathematical Biostatistics Bootcamp series. You can watch them on a YouTube playlist anytime you'd like, and then the course is offered about every 2 months on Coursera, and I give the link here. In addition, the course notes are on GitHub. Let's talk about probability. So given a random experiment, say for example rolling a die, a probability measure is a population quantity that summarizes the randomness. I want to emphasize this word population here. What this means in the die roll context is that we think of it as an intrinsic property of the die, not as something that is a function of a simple set of fixed rolls of the die. So when we talk about probability, we're not talking about something that is in the data that we have, but as a conceptual thing that exists in the population that we would like to estimate. So let's be specific about the rules that probability has to follow, so-called probability calculus. First of all, probability operates on the potential outcomes from an experiment. For example, when you roll a die, you could get a 1, or you could say the roll was in the set 1 or 2, or the roll was an even number 2, 4, 6, or the roll was an odd number 1, 3, 5, and so on. So the probability is a function that takes any of these sets of possible outcomes and assigns it a number between 0 and 1. You have to have the rule that the probability that something occurs, in other words, that you roll the die and you get a number, must be 1. And then the probability of the union of any two sets of outcomes that have nothing in common must be the sum of their respective probabilities. So take for example, when I roll the die, one possible outcome is that I get a 1 or a 2. Another possible outcome is that I get a 3 or a 4. Those two sets, 1 and 2, and the other set, 3 and 4, are mutually exclusive. They cannot both simultaneously occur. The probability of the union, that I get a 1, a 2, a 3, or a 4, is the sum of the two probabilities. The sum of the probability that I get a 1 or a 2, plus the sum of the probability that I get a 3 or a 4. It turns out that these simple rules are all that are necessary to generalize to all the rules that we think probability should follow, and this was discovered by the Russian mathematician Kolmogorov. Here are some of the rules that probability must follow. Some of them I stated already, and some of them are consequences of what I stated already. The first is the probability that nothing occurs is 0, so you have to roll the die. Something has to occur. You have to get a number. And that's similarly related to the probability that something occurs, that you do get a number, is a 1. Something that we intuitively seem to know is the probability of something is 1 minus the probability that the opposite occurs. So the probability of getting an even number when I roll the die is 1 minus the probability of getting an odd number, because the odd numbers are the opposite of getting an even number in the context of a die. The probability of at least one of two or more things that cannot simultaneously occur, we call sets of things that cannot simultaneously occur mutually exclusive, is the sum of their respective probabilities. This was part of the basic definition that we outlined in the previous slide. Another consequence of our probability calculus is if the event A implies the occurrence of the event B, then the probability of A occurring is less than the probability that B occurs. And this is kind of a tongue twister to say, and it seems a little bit conceptually hard. However, if we draw a Venn diagram, it becomes very simple. The event A lives inside of the event B. So when we talk about the probability of A, we talk about a number assigned to this circle, A. And when we talk about B, we talk about the probability assigned to this circle that includes the area of A. So it would make sense that the probability of B was larger than the probability of A. So I think we intuit this very easily. For example, the probability that we get a 1, the set A, is less than the probability that we get a 1 or a 2, the set B. Then this final bullet point is very useful. For any two events, the probability that at least one occurs is the sum of their probabilities minus their intersection. Again, this becomes very easy to visualize with a Venn diagram. Here we have the set A, and we have the set B. If we add their two probabilities, you see that we've added the intersection in twice. Once when we added in A, and once when we added in B. Since we've added it in twice, if we want the probability of the union, we need to subtract it out once. The result of this rule is to say that you can't just add probabilities if they have a non-trivial intersection. And we'll give an example of that in a second. The National Sleep Foundation reports that around 3% of the American population has sleep apnea. They also report around 10% of the North American and European population has restless leg syndrome. Let's assume for the sake of argument that these are probabilities from the same population. Can we just simply add these probabilities and conclude that about 13% of people will have at least one sleep problem of these sorts in this population? So the answer is no. The events can simultaneously occur and so are not mutually exclusive. We think that there is a non-trivial component of the population that has both sleep apnea and restless leg syndrome. So to elaborate, let's let A be the event that a person drawn from this population has sleep apnea, and B be the event that they have restless leg syndrome. Here we think this intersection is non-trivial, and so if we were to add the two probabilities, we would believe we will have added it in twice, and it would need to get subtracted out to find the probability of the union.